So my name is Scott, and I'll be talking about the experiments I've done kind of with a little, over the last few years with modeling Greek grammar. This stuff I've just done in my own time, so I kick at it every year or two and keep coming back at it, and I want to share with you kind of insights and results I've achieved and where I hope to go. So I want to talk about the different types of problems that we see in grammar in general, and then to kind of share, what would I really want in some kind of system that will help me and others do linguistic research, to really push forward in Greek grammar and what we can learn about Greek, but not only Greek, also ancient languages like Latin, Hebrew, and so forth. And then I'll share with you the different experiments I've done and what they look like. So in general, what I'm looking at here is what's called corpus linguistics. So essentially dead languages, we have manuscripts, and the language that we're studying is no longer vernacular. People don't speak it except as exercises. And so over the last, couple decades, recently a lot even more, we get people putting these texts into digital form. Scholars will transliterate manuscripts like this, and we have XML data usually that's pretty accurate, like where you see holes in there, they might even mark specific letters as reconstructed or filled in. Sometimes they normalize the spelling, so it's kind of like classical Greek, Plato style. And then there are different levels of analyses as it starts to build up, right? At the base level, you have the different types of characters, letters, and symbols that represent sounds and numbers and other things. Greek has a lot of accents and breathing marks. They didn't actually appear in Greek script until, I forget the years, but a few hundred AD or something like that. And those marks have meaning. They indicate certain things about words. They can be used to disambiguate. In the writing system, they're used to represent different sounds. So, there's some anecdote about this ancient Greek orator who, if you pronounce the word but you use a different accent, it totally changes the meaning. So instead of after the storm there was a great calm, he said after the storm there's a great weasel, and everybody burst into laughter. And the only difference was the accent. So marks have a lot of significance, and as you kind of start building up this hierarchy of analysis or understanding, it's kind of like there's an intuitive notion of what the script is representing, and when we go analyze it really closely, in our day we kind of reconstruct what we think it is. And so there are different sounds, and we reconstruct what we think Plato might have spoken based on misspellings and lots of other very minutiae. And it's really interesting. It's fun to look at that, at least for me. And you also see when you put two words next to each other, Greek likes to contract stuff and elide and all these sorts of things. So we don't typically say cannot, we just say can't, and Greek does that all over the place. And so you see changes of sound within a specific time period. So Plato would have just spoke, and those changes would have happened within his time. But then if you go across, Homer is the oldest Greek we have, down to, let's say, New Testament Greek or early AD, you see changes where Homer would have separated two vowels, but they contract into a single vowel hundreds of years later. And then Greek really is crazy here. So in English, we have different forms of the same word. So she, her, and stuff like that, or I am, you are, and that sort of thing. Well, M and R are kind of the same word, but they look different. And so you multiply that times 10 or 100, and you get Greek. So this little chart here is showing some different ending patterns that the same word could use. And then so people categorize what are the different ending patterns, and then hey, this word has this pattern except in this one case. And so there's a lot of rules and exception to rules that start to arise. And then when you start putting words together, you start getting things like parsing parseface, right? With trying to hey, is this word the verb? Is it modifying some other thing? Do these two words agree? And sometimes parsing is really difficult, as the complexity really explodes, right? the number of combinations of words as you get in distance really just flies up exponentially, maybe even worse than exponentially. And so there are these texts, since they're all limited, people are interested in them. Like, people want to study Plato and really get into it, and the main text that people beat to death is the Bible. So the Greek New Testament has been analyzed over and over and over since its existence, and similarly with the Old Testament or the Hebrew Bible. And like, how long does that take? Well, if you analyze specific forms and say, hey, this is the subject form of this word and this is the object form, each word essentially, do I have a cursor? Okay. Each word will have like a code which indicates, hey, is it nominative case? Is it plural or singular? Is it talking about more than one or not? And it's just kind of like a click fest. If somebody creates a tool and then you just go and click and choose which one it is. And that type of analysis for just specific words, not connecting the words, takes in the order of months, maybe 3 or 4 months for the New Testament for a scholar to do. Full-time, half-time, somewhere in there. Structural analysis is years. Like Old Testament, Hebrew Bible, people have spent their life work, 40 years creating it, and not manually, but also using some amount of computation. Problems you run into, well, is consistency. Hey, you started tagging this thing this one way, especially structurally, and then later you decide, well, I kind of want to even change my model. Like, you have to invent all the different categories ahead of time and then have somebody go and pick which word belongs in which category. But maybe down the line you realize, hey, I don't like my categories anymore, so I want to go back. Well, I just spent 2 months categorizing it this way. Am I going to spend 2 months going back through and changing it? I've done this kind of work. It's slow, and these are all the problems I personally experienced. So I kind of think to myself, well, I kind of like using computers to help similar things. It seems like there are patterns that we're finding, so why can't we find a way to express this pattern precisely and just have the computer find those patterns and then sort of tag them with that pattern? And I'm specifically interested in human-directed, a human is the one that's picking the category. So I'm shooting for more precision, more accuracy than a human manually going through each word and doing something with it or connecting sentences. So with machine learning, I find that very exciting, but it's like approximating human level precision, but at a larger scale. And so I think it would be useful to have machine learning or clustering algorithms or something to find patterns and then say, hey, this might be a pattern. Does this mean anything to you? And you're like, oh yeah, it does actually. But I'm hoping for more precision in less time. And so back in 2013, we've had a couple of hackathons at the company I work for. These are all my personal projects, though, not related to my work and my day job. And there's a type of syntactic structure called role and reference grammar that I was interested in at the time. Think of it like a Unicode of syntax. So Greek has very specific ways that they order words and how they combine together. Role and reference grammar shoots for a type of categorization above all languages that all languages can fit underneath, and allows you to compare and contrast how languages express the same function. So at the top is like the function. What is the person doing when they're expressing this stuff? And then it's kind of like how. It's separating the what they're doing from how they're doing it, so that way you can compare the how across different languages using the same function. And that was really interesting for me because of I have this Greek thing and I go up into the how, I could come down into another language and get a really precise literal translation and even do crazy manipulation of it. And so this hackathon, I used existing morphology and syntax databases. And the results were, well, I was using C#, and if you've ever done a lot of tree transformations in C#, it's not a very fun thing. And visitor patterns, I just looked at some visitor patterns I hadn't looked at in a long time, just a month ago, and they're really bad compared to something like Haskell. Or, don't take my word for it, the Rosalind team, Eric Lippert's blog, he mentioned that they didn't trust themselves to write visitor patterns, so instead they wrote XML that they used to generate visitor patterns. So to me, it's like a sign. XML is better than visitor patterns. It's kind of very scary. On the data side, what I found is, so I mentioned consistency and preconceived categorizations. In this hackathon, I found myself a team. I actually had 3 linguists with me and another guy. And we were undoing a lot of the choices that the people creating the syntax tree had made in order to do this other thing. And so that was dissatisfying because I don't want to spend time learning what this other person did only to undo it and redo it in a better way. So I'm like, I'll kind of leave that aside. And so, before this time and continuing on, I really ramped up. Hey, Okasaki's purely functional data structures. Let's learn standard ML. It's like, we'll use .NET at work. Let's use F# and Haskell. And I sort of really fell in love with Haskell. Played around with more specific stuff. Coq and Idris, the ability to prove stuff is really game-changing for my mind. It's like I can prove things and actually, have this really strong logic behind it. And so I really loved that. Culminated in Agda is probably my favorite out of that bunch too. And also studying the grammars more closely. So when you look at an existing grammar, they just go all the way back, to letters. These are the different ways we write letters down and how it's changed over the years. This is how the sounds come together. And all the later ones, as I kind of had talking about a hierarchy. Well, the later ones depend on the choices you make earlier. If you chose to say this vowel is pronounced with an open mouth, that's going to affect your later rules, because sometimes they make a rule if you have this vowel that's open followed by this kind of a consonant, then this thing happens. Well, if you decide that maybe that vowel wasn't pronounced open at one time, then it's going to change the results you get. And what we've done typically for New Testament and some amount of other ancient languages, we typically do word level analysis. We've done a lot of that, and then some structure. Often the structure is partially automated. But we really haven't categorized sounds and how sounds change over time. People talk about it, but they're buried in these grammars. So I thought, well, why not try to start encoding some of this stuff really precisely? Let's go full force, jump right into Agda. Dependent types, we get pretty much arbitrary precision with a little star up to some philosophical limit and that type of thing. My personal problem is, I'm just learning Agda, so here I try to do a really complicated thing. And so it's I don't have time to get 2 PhDs to know how to write Agda, so. So it was successful, but then it was slow. And this is the crazy idea I had. Writing Agda code as data. So I took XML files, the entire Greek New Testament, and just generated a list of all the characters. And then for each character, you see I took the UTF, right? Agda, you can just use UTF-8 characters in there, or Unicode code points. So I just dumped the entire set of there's 200 of these pre-composed Greek Unicode characters, and I just took that, and then for each one of those, I used the UCD database to create a really precise type model that encoded all of this vowel can't have this accent, but it can have this other one, and encoded all that information, and then sort of type check the New Testament. And I thought, wow, that's great, and guess how long it took to type check? It's hour. It's an hour for the whole thing. I'm well, that's kind of slow, and all I did was check that the marks were correct, basically. But it was a fascinating idea to me, and the reason is because when you get into dependent types, you can just push anything up into the type level, and it's how do you know the difference between running a program on some data or having it available at type checking and just type checking it. You get similar things where people encode Conway's Game of Life in C++ templates or something. It's well, do you run a whole game at compile time or not? And so for me, the difference between runtime and type check or compile time is, do you have the data available to you at type check time? It's well, I do. I just got to get it in the right form, and boom, I have this thing, and I can write proofs not only about a model. Usually Agda proofs are about some inductive model that they create. This inductive model represents Cauchy sequences or something, and now I can do stuff with it. But this is I have literal text that represents something from the world, and I can write a proof that I have created a categorization that accounts for everything that happens in that text. And to me, that was really attractive. I had to set aside this thing because I was I don't know if I want to go this route. Too long, too complicated for me right now. But I'm coming back to this idea. And if you think about it, we like JSON a lot these days, and JSON is just sort of the object structure of JSON or JavaScript pull out. And then people are well, it doesn't have type information. How do I know if it's the right structure? Well, then you write JSON schemas or stuff, or you have this XML and XML schema. But imagine a world where we have data that we can express all the data as terms, and then we have the separate thing, which is the schema, which is a type. And if we have something like Agda, we can have really precise human-readable data that we can check that it's actually precise, and that's just the type of the thing over here. And to me, that idea is really fascinating. I think somebody should do more with that. So, okay, let's do another experiment with Hackathon. Now it's like, well, okay, I'll take a step back. Let's go down to Haskell. And I'm going to encode, there's all these rules about sound transformations, and so I took 4 of my linguistic colleagues that knew Greek really well and Hebrew, and let's just crank out some of these rules and like throw it at some text and see what happens. And what happened is like, man, Greek phonology, they call it, well, phone, which is sound, so you got to kind of know Greek to know Greek. But so we took all these phonology rules, and we realized that it's hard. Like we're trying to type check the grammar. Like, what are they talking about here? You say A plus A, an A plus an A gives you an A, but is this resulting A the same thing? Because sometimes they have lengths and sometimes they don't, and like, well, sometimes we're adding the lengths of vowels back together, and then you have like reconstructed pronunciation. So there's a lingual using your tongue followed by something else, and so actually most of that hackathon time is spent trying to like understand, like what do you call that? When you try to figure out what somebody did based on this encoding, and it was hard. And sometimes there's consistencies, like the word for God, theos in Greek. The E followed by an O sound usually contracts to this U sound. And then it's kind of weird. They say it doesn't contract in classical Greek at this time because they postulate an earlier S sound between them, and then the S sound kind of dropped out and we're left with this other thing. But in another case, they say that things, it's like they contradicted themselves later on with another rule that seemed to say the opposite. And it's like, well, I don't even know what. So that was just kind of a kickoff of a much bigger project, and that's kind of the core of what I want to show you toward the end as the talk goes on. So we're going to deep down into like lenses and crazy prism stuff. So we presented at the Society of Biblical Literature last November. And so my idea was, let's just go all the way to the root. I'm not going to use anybody else's data. I might look at grammars and be informed by them. But the choice that we're going to make is I'm going to build this big structure up, and I'm going to do it in Haskell at runtime and just use kind of this Haskell to deal with the transformations. But the thing is, it's like I want to see what I did. And so I want to see, for every given category I make, I want to see every single word that has that category. And then I also want to, if I'm just reading the text in order, I want to like be able to click on a word and see, well, what are the categories that this word has? So I serialized it out to JSON. It was a really nasty serialization. Forgive me, please. And then I can view it in the browser. Wrote some JavaScript and React to kind of test what that looks like. I'll never do that again. PureScript or Elm something, please. So the problem is I'm essentially having to, it's parsing. Like I expect to see this pattern somewhere, and it's kind of like parsing. Like parsec where, hey, I want to find this letter followed by any number of these things and then followed by something else. It's really similar to that. But I didn't want to do this gigantic one because I'm trying to like discover it at the same time. And parser combinators, especially with something like parsec where you don't have backtracking by default, if you do it wrong and you have this hidden ambiguity, the types aren't really helping you there. So I've been bitten by that quite a bit. And so what I wanted to do is very minute transformations. And for me, the thing that was really cool when I started thinking about lenses is lenses can change the type of something. So if you have a structure and you can essentially, you have an isomorphism between that and like a tuple, like A and B, well, essentially you can like transform a structure so that you have this piece over here you're not going to change, but you're going to change this piece over here and swap out with a different type. So I can go from like the entire Unicode character set, which is, I don't know, 1 million characters or something, and especially if you do a 32 code point, it potentially could even be anything in the 32-bit space, down to the Greek character set, which is like 50-ish. So it's like, well, I don't want to keep pattern matching or something, like rechecking that I'm not outside of that space. So I just want to go down from Unicode char down to a 50 size, like some type or something. And then, well, at that time, I want to break it apart and change that type. So the cool thing for me was to discover that prisms are just the same idea. You have an isomorphism to an either. Instead of A and a B, you have an A or B. In the prism, you just can swap out like the A with a C, and then you get a C or B. And traversals, it's like, well, you have like a list of something or a structure that you can kind of imagine like a list, and then like walk through it, keeping the transformation, keeping the structure, but then swapping out all the pieces of something different. And in each case, the goal is like I'm changing these types, so the types are getting smaller and smaller, more precise, and each one kind of gives more information. It's like I go down from Unicode. Well, I'm not dealing with every Unicode character. I'm really dealing with only Greek ones. And then I'm also kind of reducing the size there. So to give you an example of this, like if I just have a basic structure of like a list of works, and when I mean work, like a textual work, like a book of the Bible or Plato's Republic or something like that, and that's composed of different properties like the author, the title, and that kind of stuff, cross like a tuple with the list of words, and a word is really like word properties and like a list of letters, or maybe it starts out with like a list of Unicode chars or something. And so the cool thing for me with lenses is like, well, I want to swap out letter and turn that into a vowel or a consonant. So what I can do is, well, use this f function down here, and the goal type at the bottom I want here is really that where the letter got swapped out. So I have no Unicode anymore. Unicode is fine for data transformation, but this, it's very much the wrong choice. It's way too huge, way too complex, lots of rules that I don't like. And so I can focus on that function and use this path, which is like a composite, right? I traverse over this list, I take the second thing in this pair, I traverse over the inner list, and I go, focus on the second half of that, and I traverse over that, and that gives me the path to the structure that I want to change, and then I can use the lens over, and then voila, I just kind of get this as the result. And the super cool thing is that lenses and prisms and traversals are functors, they are applicative, so you kind of get this applicative semantics that kind of traverse where the, if you have a function to like a maybe, that maybe, instead of being a maybe be deep in this nested structure, the maybe can pop out. And the way you do that, well, the lens is the thing, is like the applicative thing there, so you don't even need the over. You just use the lens path itself and apply that, this function f over that in my structure. And so I use that. If I have a function that is like absolutely equivalent, like letter is evenly divisible into vowels or consonants, and I account for every case. It's like a total function essentially. But maybe I have some other case where I have an unexpected error case. And so then I want to kind of check. I'm essentially categorizing. So think of vowels. So in Greek, if you have an O sound followed by a U sound, you get it combines into a single sound. It's not like oh, ooh, it turns into ooh, like in soup, S-O-U-P. So, but not every combination of two vowels turns into a single sound. So sometimes I want to deal with vowels combining together, but then have these cases where they don't. And so in that case, I can have a sum type of all the possible combinations of two vowels as a very finite set. There's only like 5 of them, I think. And then have single vowels, but then I have an exact representation of what I'm interested in and what I expect to see. And so when I run or whatever, this lens thing across this structure, if I get the nothing case, well, I use more like an either with an error and tells me what the error was and all that jazz. But essentially I kind of like have cut off all the stuff I'm not interested in, and now I have this smaller cardinality set or type that's representing more information. So this was a lot of fun. This idea I found very successful, and I plan to continue this idea. So essentially what I'm starting from, Unicode, compose, I decompose them because Greek typically has like all these accents on a single code point, and then like they break down to like 3 code points. Greek has uppercase and lowercase, but they also have this final form, and S at the end is different, looks different than an S in the middle of the word. There are lots of different marks, 7 marks maybe, and they actually divide into 3 categories: accents, breathing, and how they divide into syllables, and then you have vowels and consonants and syllables, and then I started to get more into phonology a little bit, not a lot. So just to give me an idea of kind of what happens. So if I have this list of the works, and then it has a list of words, and it has a list of characters, whether it's a list or not doesn't really matter. I have this function, I want to take a character, and maybe it turns into what I call concrete letter, where it's a sum type where uppercase is a distinct some branch type, then like you have capital A, lowercase a, capital B, lowercase b. So they're all separate. There's like 50 of those. Or it's a mark because I kind of have a decomposed thing. The next step, and that's a maybe. It's like, well, maybe I might not hit the end. And so I can apply a function to maybe and just use the lens itself, the lens, prism, traversal composition as my path and just kind of make this transition. And now my type has changed. I can do it again, a concrete letter or a mark. Well, it turns out that what I'm expecting is always a letter followed by 0 or more marks in that pattern. And this type up here doesn't allow that particular case. So really I need to do something like a fold where I'm taking a list of this pattern and I'm turning it into maybe, if it parses correctly, I'll get a list of this pattern. And if my expectation is wrong, I'll hit an error case as I go along. But if I don't, then I kind of like, I've succeeded in reducing the structure. Now, concrete letter, like I said, is really more like what I'd call an abstract letter, for lack of better names, concrete abstract, I don't know. Now I have alpha, beta, gamma, the Greek alphabet. I'm not distinguishing case in that particular sum type. That's 22, I can't remember. But then I'm separating as a tuple the case as a separate thing, and then whether it's a final form or not. I want to distinguish between it is final, it is not final, or this letter doesn't even have a final form at all. So 3 cases. This kind of breaks down cleanly. So I apply that, next stage. Okay, and now I have case here, but if you think about it, I don't come across Greek that all of a sudden has an uppercase right in the middle of the word and the rest of it's lowercase. Really, it's a pretty regular pattern. I have all lowercase in a nicely edited text, or I have an uppercase followed by the rest lowercase. So what I can do is break down this case at the letter level, get rid of it, and pull it out into a word level property that's now capitalization. Is this word capitalized or not? And so I do that. You get a little more complicated function because I want to deal with, well, I don't know what properties are here. So it'd be kind of nicer if Haskell had like a row polymorphism kind of a thing. Yep.
How significant is case? I mean, I don't know any ancient Greek grammar. Is it used to denote proper nouns or anything like that? Or?
It can be. Mm-hmm. To me, so there's with Greek, it's like, hey, we're going to do some analysis of Greek, and then they say, well, I'm just going to ignore all this data, like accents and stuff. So some accents have meaning or not, and I just wanted to say, hey, I accounted for everything. And so then I can build up, and if I have this type, at this point, you know, I've accounted for all of the marks and information at this layer, and then I can just keep on progressing up. And you can kind of think of, you can go back, right? It's easy enough if I know a word is capitalized or not. I can either make it capitalized or not. And then I can also make choices. Well, maybe I want to create an edited text where it's all lowercase, or I change it into, you know, some other type of form. But having that information, it's more just information preserving rather than being, hey, this is, I want to study Greek so I can learn what cases they used, you know.
So you're just conscious about retaining as much information from the original sources?
Yep, and I want to retain the information, but I also want to retain it in a way that's useful for me and it's precise. So really, the capitalization at the letter level isn't that interesting. It just happens to be a convention of the way it's written. But more interesting is like, is this word capitalized or not? Because then you start asking questions, well, I capitalize words at the beginning of sentences or proper nouns, or I don't. And that is a more interesting property than whether in each individual letter is capitalized.
One more question. So I don't know about Greek, but Latin, ancient Latin, they were not consistent about spaces between words. It wasn't always possible to determine when one word finished and the next one starts. And you could actually sort of significantly change the meaning of the sentence. And I think Hebrew suffers from that problem as well. So how do you know that your word boundaries are correct? Are you given the data when it's already been, the sources that have already been cut up along the word boundaries? Yeah, so as I kind of worked on this, I realized that pretty much every text you come across is kind of a different problem, because some texts will be, you have this really raw form and you just want to expose the information that you have, and then you can talk about from a more known, better formed thing, hey, these are all the words that occur over here, what words might be disambiguated out of this more ambiguous mess of words that are all jumbled together and stuff. And so for me, I want to encode all that information, but a text like that would be a different problem and might, like I can reuse each of these pieces, because it's just like, well, it doesn't matter what other properties are around. All I'm really looking at is, does a letter have a capitalization or not,
or case or not, and then move that to a word level property. So if the input text didn't have that, well, I wouldn't use this little utility library, this function, to do this transformation. So that's kind of the idea. Yep.
So are you using an addition, like what is it, the Teubner? That's one of the standard ones for Greek text?
In terms of like...
I mean, I partly to answer that question, because there's nothing original, really. Maybe like papyrus scraps. So
yeah.
I would assume that you would use some kind of scholarly addition that would solve most of those sorts of editorial problems, or like shove them into some gigantic apparatus criticus that requires its own parsing. Yeah,
in my mind, it's like, well, I want to do everything. I want to take an existing scholarly work and like validate that it's actually true. So something like Smythe's grammar, where he makes a lot of these rules, I want to see where can we actually see this pattern occur across all the input text and like validate, is this an actually true statement or not? Or to make it more precise, sometimes you'll read, sometimes you see this pattern occur. Well, that's kind of cool, but it's more an observation on his part, and I want to make that precise and say, well, I know exactly where it occurs. It occurs in Plato, Republic here, it occurs here, it occurs here, it occurs there. And I want to use this kind of type transformation to build up that kind of database, or this, it's like a type database or something.
Where do the texts come from? Like
so this text, so this particular text is an edited version called the SBL, Society of Biblical Literature, Greek New Testament, and that's what I was using for this particular case, not this rule, but for this particular project. But this year I'm kind of working on expanding that to using some of, as much as Perseus' stuff that I can, and there's some like papyri.info, and there's like other Greek New Testament manuscripts, and some OCR'd different things from early AD texts. And so each of those kind of presents a different problem. If it's like an OCR text, then I can kind of use this to help correct problems. Like I noticed here that in an analogous case here, there was a grave accent at the end of a sentence. Well, you don't put grave accents at the end of a sentence, just because that's not the convention, and that stuck out because there's like one grave accent at the, I could put together, hey, is this the word at the end of the sentence, and is this, what accent type is it? And I saw one grave accent at the end of the sentence, and I could correct that error. And so it's possible I could use this for correcting errors, and that's kind of the idea. But to in this case, this is a little bit like I can use a validation step that if I have a final form, it's really at the end of the word, so I check that this list ends in a final form, split down, like I said, a letter into vowel or consonant, and so on and so forth. And so as I was doing these, kind of writing in Haskell, this idea is coding this blindly. I expect to find this pattern, but I also want to dump out all this data that I have so far. And so that's what I did. I want to show you a little bit what that looks like. How big is this? So I created this site. So as I do a transformation, I suck out the data, parts of the data that I want, and then dump it out into book form. So this is like one of the books, a letter of St. Paul to Philemon. And then I can, for every word, I can get some of the summaries. I imported an existing morphological hand annotated thing. So this system is strong enough that if the data aligns properly, if it's like they analyze the same text that I have, I can just take existing analyses and throw this into the system. So some examples of properties that can be interesting, I ended up breaking it down to the syllable level. So then what I can do is I'll say, hey, this word has 2 syllables. So I can, for example, click on this, and this will show me all of the 2-syllable words that occur throughout the New Testament and kind of where they occur. Or I could say I can click on this guy and then find out what are all the different types of, how many syllables. And so this is like you might think of like a type of syllable counts or something. And well, there are everywhere from 0 syllables to 8 syllables. A 0 syllable is an elided de, where they cut off the thing. In Greek, in like Italian, they tend to write that as a single word, or French or something, but in Greek, they write this as a separate word for whatever reason. And some things like crassus is a case of like an initial contraction, and so where crassus occurs, I can see, hey, look at that. Usually this little symbol here is only on a word that begins with a vowel, and this word begins with a consonant, and so you can kind of abstract that and see where this particular pattern occurs. And the other, so that's kind of like viewing a text in order and seeing what analysis happened to be applied to each word. There's a lot more data. And this is kind of looking at all of the properties themselves, and that's kind of a lot. I kind of go from bottom up, so my little lens kind of compositions as you look at them, I start from like Unicode compose character, and then I have a function that decomposes it, and I can actually look at how, like, what data pipe through each of the cases in my function. How are we doing in time?
We're out of time.
Okay.
Over.
Okay. Anyway, so that kind of gives you an idea. Let me just finish off. So what I'm looking for in this system is I can ask questions using kind of like a parser combinator, and I account for every case I see. It's precise, and I can review the results. And it kind of creates this loop. It's like I see these results, and now I see, oh, I only see 3 cases of this question I asked, and now I can go back and create a type that only has 3 cases and like shove everything through that filter. I'm working on using Agda to write a round trip. So given a form, I can go back and prove that that thing round trips, so I have an equivalence there, usually right equivalence, because if I go from a bigger set to a smaller set, I want to verify that if I start from the smaller one and go back. There's related work. People model stuff. ICFP 2004, these guys model Latin morphology and stuff in Haskell, and grammatical framework is like its own sort of language with even dependent types. And if you go on GitHub and search for Greek grammar, you can find my site. So thank you.